Analyzing complex three-dimensional atomic structures requires projecting them onto a two-dimensional plane. The challenge in crystallography is doing this without destroying the physical relationships that define its behavior. These images show the standard approach of linear projection. We transition from the 3D unit cell of hexagonal epsilon carbide to a 2D representation along the z-axis. The physical locations of the iron and carbon atoms are compressed flat. By assigning fractional z-coordinates to the atoms in the diagram, this method successfully preserves depth data. We know exactly where every atom sits in space relative to the cell boundaries. But while spatial coordinates tell us where atoms are, linear projections distort the angles between them. In material science, the angles between crystal planes dictate how a metal deforms under stress, or how phase transformations occur in the solid state. This animated diagram demonstrates the geometric distortion. When a circular arc is linearly projected onto a horizontal baseline, the distance between even intervals is compressed and warped as they reach the edges. The projection is spatially accurate, but the angles are lost. To calculate a material's complex physical properties, positional coordinates are often insufficient. We need to supplement spatial maps with a projection that perfectly preserves three-dimensional orientations and angles, the stereogram. The stereographic projection begins by placing our crystal at the exact center of a reference sphere. We define an equatorial plane cutting horizontally through the middle and a projection pole at the sphere's south pole. This geometry relies on a property called conformality. It is the mathematical guarantee that circles on the surface of the sphere will remain true circles on the projection, keeping exact intersection angles intact. This diagram illustrates the mechanism. A generic circle labeled AB on the northern hemisphere is projected down onto the equatorial plane by tracing lines originating from the South Pole. Looking at the geometric cross-section, we can see the symmetric inclination of the projection lines. The conjugate circular section CD is symmetrically inclined to the central vertical axis. Because the arcs running down to the South Pole are equal in length, the angle phi1 exactly equals phi2. This geometric relationship ensures that the projected shape on the equatorial plane is not warped into an ellipse, it remains a circle. Every three-dimensional spherical coordinate can be mapped to a flat plane while maintaining its exact angular identity. Inside a crystal, atomic planes stretch out and intersect our reference sphere. These intersections happen in two ways, great circles and small circles. If the intersecting plane passes directly through the center of the sphere, it creates a great circle. If the plane is offset and does not pass through the center, it results in a small circle. To map a specific crystallographic plane on a 2D stereogram, we plot its normal vector, the line running exactly perpendicular to the plane. This point is known as the pole. Step 1 is to orient the crystal lattice at the exact center of our reference sphere. Step 2, extend the normal vector from a plane to the sphere's surface. Step 3, draw a projection line from that point down to the South Pole. Step 4, mark where this line pierces the equator. That dot is our pole. If we extend the plane itself to the edge of the sphere, it creates a great circle, which projects onto the equatorial plane as an arcing trace. Every point on that trace sits exactly 90 degrees away from the pole. The three-dimensional angular orientation of the crystal face is now permanently recorded as a two-dimensional coordinate. We can scale this projection to map the entire sphere. This reference image shows the sphere covered in a dense, regular grid of longitude and latitude lines. By projecting every great circle of longitude and small circle of latitude down onto the equatorial plane, we generate a standardized measuring tool. The resulting projection is known as the Wolf net, a fundamental tool in crystallography. This geometric derivation shows how the curves are formed. The great circles project as arcs of circles, and their specific radius, r, is calculated algebraically based on the trace's offset from the origin. In practice, the Wolf net acts as a standardized angular ruler for crystallography. The grid lines are typically spaced at intervals of 2 degrees. It transforms abstract spherical geometry into an actionable tool for extracting three-dimensional coordinates from a flat page. To measure the angle between any two mapped poles, you rotate the net until both poles lie on the same great circle, and then you count the degrees of separation. This Wolf net illustration shows a pole and its corresponding trace arc. As established, the separation between the pole and its trace is always exactly 90 degrees along that great circle. Because of the scaling inherent to the projection, the angular center of the circle can differ from its geometric center. On this wolf net, point B is the angular center, while C is the visual center. This diagram shows two intersecting arcs on the net. Because the method preserves angles, we can use these overlapping radii to triangulate exact pole positions based on known angular distances. The wolf's net is a precision instrument for reading orientation data, reducing three-dimensional spherical geometry to simple arithmetic. Mapping these orientations is critical because the properties of crystals are rarely uniform in every direction. They vary depending on how the atomic lattice is oriented relative to external forces. A property like the elastic modulus, which measures how a material resists deformation, changes significantly depending on the orientation of the single crystal. This stereogram shows the elastic modulus for a single crystal of body-centered cubic iron. By mapping the stiffness against orientation, we can see it varies from 131 gigapascals to 284. These variations are determined by the crystal's symmetry. We can map the symmetry operations of an entire crystal class onto a stereogram. This pyrite crystal belongs to point group M3. By plotting a general pole and its symmetry-related positions, the stereogram immediately reveals whether the structure has a center of symmetry. Symmetry dictates a material's physical capabilities. In structures that lack a center of symmetry, like lead titanate, the atomic arrangement is such that a dipole develops under mechanical stress. By checking symmetry elements on a stereogram, engineers can identify non-centrosymmetric structures and predict exactly when a material will exhibit properties like piezoelectricity. Linear projections map the spatial reality of atomic bonds, but to calculate how a metal will bend or how a crystal will conduct electricity, we need to map the angles.